Okay. Good morning, everybody, dear all. I would like to welcome to this eighth online seminar that belongs to a series of seminars for the Journal of Resilient Cities and Structures. And I assume that if you are participating to this webinar, you're already familiar with the journals and the scope of this journal. So if you are working in the field, we strongly encourage you to submit manuscript to this journal, which currently allows, at this stage, still open access publication without publication fee. So today's seminar's title is Intelligence Earthquake Response Prediction and Resilience Assessment for Building Clusters. The seminar will be presented by Professor Ying Zhu, who is professor and dean of the College of Civil Engineering at Tongji University and is also a recipient of the National Outstanding Young Scientist Fund for NSFC. Professor Zhou serves as Executive Deputy Director of the State Key Laboratory of Disaster Reduction in Civil Engineering in China, and is also the Director of the International Joint Research Laboratory of Earthquake Engineering. He was also Vice President of the Anti-Seismic International Society, ASSISI, from 2019 to 2023, and she's still currently active as Executive Committee member. Professor Zhou research focused on seismic resilience and intelligent disaster prevention of high-rise building. She has received the China Young Science and Technology Award, and she has led projects that won first-class award for technological invention and the first-class award for scientific and technological progress in Shanghai. And she currently serves also as the chief scientist for the National Key Research and Development Program. So before we start, I would like to remind you that at the end of the seminar, we will have the question and answer part, and don't forget to submit papers to this journal, because if you publish a journal paper to Resilient Cities and Structure, you could be the possible eligible person to participate to this webinar series. So we are looking forward to this very interesting presentation, and without any further ado, I will leave the floor to Professor Zhou.
Thank you, Professor Campos Malero, for your introduction. Dear ladies and gentlemen, good morning, good afternoon, good evening. It's my pleasure to be invited by our own journal which is entitled Resilient Cities and Structures. This is the 8th webinar. Today I will give the presentation entitled Intelligent Earthquake Response Prediction and Resilience Assessment for Building Clusters. As you can see on screen, I come from two affiliations. The first one is College of Civil Engineering, Tongji University. The second is we call it State Key Laboratory of Disaster Reduction in Civil Engineering. So first, I would like to show you this affiliation. You see, according to the Global Risk Report 2023, in the next 2 years, the natural disasters and extreme weather events rank number 2. If we look at the coming 10 years, the climate change adaptation, and natural disasters are among the top 3 risks. So which means after so many years development, climate change and extreme cases like disasters are those cases we have to face together. So look at China. In the year of 1988, we built the first state key laboratory of disaster reduction in civil engineering at Tongji University, which was reorganized in 2023. Under the state key laboratory, we have lots of discussion like natural disasters. Generally, in the earth, there are more than 60 natural disasters. But for our state key laboratory, we focus on the research from the earthquake, wind, fire, and added blast, flood, and geological disaster research in 2023. So today I will show you my research which lie in the category of earthquake engineering. Since this year is very important anniversary, we call it a 110th anniversary of the college. We start a new engineering hall. We call it multi-disaster reduction engineering hall, which is shown on the screen, which was grand opening last month. Next time, you are welcome to visit our multi-disaster reduction engineering hall. Here comes the contents. First come the first one is the social demands and challenges of the new times, especially after the COVID. First, let's look at the comparison of the bounds of Shanghai city. You can see we call it high density buildings or building clusters are the new trend after the 30 years construction. If you look at the urbanization of China, goes from 26% in 1990 to 56% in the year of 2023, and which means majority of China become a urban area, and for those area, the buildings are first time have the photo. We call it the ID of the buildings. It is reported by the newspaper that 1.4 billion people in China possesses 600 million buildings. And here comes the new research demands. The first one, if you travel around China from Beijing, Shanghai, Guangzhou, and Shenzhen, for example, for those buildings about 100 meters tall, in Beijing they have 62, in Shanghai and Guangzhou around 200, and Shenzhen maybe doubled. So those are really high density building clusters in those mega cities. If those cities have hit by the earthquake or natural disasters, there will be the big loss for economy and people's life. So this first demand, our research have to change from traditional individual building to building clusters. The second one, from the recent earthquake record, like the Tohoku earthquake and the Turkey earthquake in last year, you can see the tsunami and blast and other secondary disasters are followed by the earthquake. So now the research have to change from traditional individual disaster to multiple disasters. And let's look at our research objectives for the disaster mitigation. The input or disturbance, we call it multi-disasters. From traditional method goes to joint probability density function research. Our systems goes from individual building to, we call it complex systems or even system of systems, SOS, which means we have to build the complex network system model. And our control objectives change from traditional safety to, we call it resilience, which means faster emergency response, lowest repair cost, and optimal recovery paths, etc. From those research, you can obviously, we have to use the mega data and big data and interdisciplinary research. Those are changing of our research demand for the new times. Let's come to our topic today, earthquake response prediction and resilient assessment for building clusters. Here comes the three questions. First one, how to accelerate the response prediction of building clusters. I will introduce a new algorithm by use of AI, we call it phase size former. Second, how to achieve transfer learning from one building to building clusters. So we train a model, large parameter model, we call it SatsGPT model, which just completed this month, last month. The third question, after we have so many data of the response of the building clusters, how to read building cluster resilience, we call it resilience rating system. So today I will explain one by one. So number two, how to accelerate the response prediction of the buildings. Here is an example of the library of Tongji University. If you enter the main gate, you can see the statue of the Chairman Mao, and then behind it is this library. For this numerical model, I mean the Abacus model, the elastoplastic analysis of this model by use of Abacus will take 3.5 hours. It's a time consuming. Say nothing about 2.2 million million buildings of Shanghai. So we really look at our research algorithm, which is called finite element method, which is proposed by Professor Clough in the year of 1960 in the area of airplane by use of finite element method. I think the audience today are familiar with this method. It's come from it's divided the structure into elements, and those elements are connected through nodes. So three kind of equations are help to have the final result, which is geometrical, physical, and equilibrium equations. So from this theory, we have many commercial and research software to do the analysis of the building. Behind this, we agree the scientific computing method is controlled by mathematical and physical equations. So here comes the new paradigm by training our AI algorithm. So data-driven and physical-driven, physical informed and data-driven are very important by using of the finite element method. We call it AI-powered method, right? So still using physics informed and data-driven methodology. So based on this understanding, let's, on the other hand, let's look at the AI. What's the core elements of the AI? We call it data, algorithm, and computing power. First, I think where the high quality or even we call it scientific data comes from. So we really look at the State Key Laboratory. We have performed more than 1,500 shake tables of various buildings, important structures. So those are valuable data by using of experiment parallelism. And the second are those data come from finite element analysis, like Abacus. In the laboratory, we have an important software called NOSA CAD. This software comes from CAD easily to build a model, but can transfer among the PKPM, subdusort, and ETABS, and LCDNA, and even HyperMesh. So it has various of the numerical analysis. Those are data. We call it scientific data or high quality data, which is verified by the shaking table test, by the in situ structural health monitoring data. So those models are very important for the further analysis of AI. And the second core element for AI is algorithm. Actually, this is the development of classic algorithm by AI. You can see AI from up and down. It comes from beginning as a knowledge-driven, goes to now is like a kind of a data-driven. Especially from machine learning to deep learning, I started to look at the AI as a tool right 10 years after Wenchuan earthquake, which is started from 2018. At those beginning, I come from by using of AI technology to look at the local damage. I call it damage detection algorithm. So I using of CNN to introduce the attention unit, Siamese SDN, at least. But with the development of transfer is popular, right? It's a GPT, it's a T transfer. It's come from the natural language processing, like a BERT, GPT. I think it's very interesting. I started to look at the transformer. So today I will introduce this part is structure response prediction algorithm. And also for kind of a diffusion model like Sora, definitely it can be used for intelligent design algorithm. I also started like Archi diffusion and structure diffusion have two publications this year. But today I will generally look at the transfer to use for the structure response prediction method. Here comes my idea. You can see for engineering or earthquake engineering, we learn from the natural language processing. Transformer is shown as its advantages shown as advantages in the field of natural language processing because of this multi-head self-attention. There's the important reference is entitled "Attention is all you need." This is the core. By introducing this sequential architecture in transformer have this parallel architecture among which the multi-head self-attention is the core. Because of this self-attention, it has the following three advantages, at least the three for advantages. The first one, it has stronger parallel computing power. Parallel computing, which we use, we try to use many years for finite element analysis, right? So this algorithm has stronger parallel computing power. Second, it has stronger ability to capture long distance deficiencies, like a sentence, like a sequence, right? Sequential. This is important. And third is to solve the gradient explorer and vanish problems for analysis. So earthquake is also a kind of a time sequence, right? So it has a similar sequence based for the computers. So that's why I think transformer is very good for this problem. And then we propose this phase size former. For this, you see, former is transformer. Size means seismic. Phase means physically informed. So for this core algorithm, which has three parts, step one is auto-regression. Step two is structure information extraction. Step three will be phase size former. By using of this phase size former, it can go to the analysis or prediction, and the future can be used for the can be used for the structure damage assessment and has structure has monitoring and seismic resilience assessment. So I will introduce this later. Okay, first step is data-driven auto-regressive iterative forecasting. This is a chain strategy. Obviously, it can comes from the structure information, input earthquake, and then have the structure response goes to the first iteration and go to the next one. This is an input output regression. The second is structure information extraction. So as we are all earthquake engineers, we are familiar with structure dynamics. That's why for us, computer science engineers can not have this kind of analysis because we have this background of structure dynamics. So we train the model. We also use the multiple degree of freedom models results as the response as the results to train the model. So this is a very important information extraction. And then step three is phase size former model of the structure. As we do the analysis of like Abacus, we have pre-process analysis and the post-process, right? So now it goes back for this phase size formula. We pre-process, we have the token embedding and positional embedding. Like people eat food, the AI eats token. So token embedding is your first step for the pre-processing. And the second is the core part. We call the size block, which among which the multi-headed self-attention mechanism is embedded. That's why it become efficient, can accelerate our analysis because of this multi-headed self-attention mechanism. And then post or process using multi-layer perception. Oh my God, perception, and they're using a three loss function. So this paper was published by the Journal of Engineering this year, which is for your information. And this is the basic components of the structure of the size block and the mechanism. And when we finish this, we will do the experiment. Compared to traditional physical experiment in the shaking table testing division, this time we're using our computers to do the experiment. We introduce 200 ground motions in total, 186 artificial views, and 14 ground motions recommended by the local codes. The aim of this research is to accelerate the earthquake response prediction of the finite element analysis. So we define the time acceleration ratio, which means how efficiency of our analysis by use of AI. Here comes the prototype buildings. As I showed before, we do appreciate for the State Key Laboratory, they donate many analytical models. Even for the campus, we have 4-story mission structure, 11-story reinforced concrete structure of library, and 21st-story reinforced concrete structure, etc. So here comes the results. One of the results as an example. I think the first important for the analysis is accuracy. So R is very, very important to be evaluated first. You can see the R comes from 0.95 to 0.99. We think the R is acceptable. And the eta is efficiency. It goes to more than 9,000, even 10,000 faster than traditional numerical analysis. I mean, the finite element analysis, and not compared to the simplified models in the past. It can have very good, time history prediction of the acceleration, velocity, and the displacement, and similar high accuracy were achieved for other cases. And we also compare to the old algorithm, I mean the LSTM model. By using of this LSTM model, you can see the R. Of course, the phase size former have higher accuracy compared to as LSTM. Also, we also compare the time history prediction of the nodes. Okay, here is the first algorithm. You can see for our by using of the AI, especially the transformer algorithm, we call it physics informed deep learning based real-time structure response prediction method, which is a phase size formula. It's a core algorithm. The analysis of the library can change from 3.5 hours to only 0.5 seconds to obtain all the responses of the nodes quickly. And here comes the second question: how to achieve the transfer learning from single building to building clusters. And let's look back again for natural language processing, which is a ChatGPT. Since we have using the transformer, we use a token, we use a transformer, and we can pre-train the foundation model and to have our own, we call it generative pre-trained size former as size GPT. After months work, now we have this size GPT as a physics-informed data-driven large model for real-time seismic response prediction, which is uploaded as archive for your information. And let's see the size GPT foundation model for building cluster earthquake response prediction. For all the kind of this kind of large model, large foundation model, it has a standard step. First one is a large scale data set generation. For our case, for earthquake engineering, we have 3 kind of data. First one is the finite element calculation data. Second, shaking table test data. Third, very important in our field, we have the finite element software, right? We automatically generated finite element model data and do the data processing to make it become high quality disaster response data set. Second step is pre-train the buildings, supervised learning. And the third step is fine-tuned buildings. It helps the model learns have the ability of transfer learning. Okay, here's the first step. We have the refined model. You see lots of models, analytical models, and those analytical models of the bound in the past. We have a lot of analysis. And oh my God. And also we use the shaking table test data from the state K laboratory, which I show at the beginning. And then we're using the OpenSeas and as a software to generate finite element data, and then using API to do in the software and in the design software to verify the model accuracy. So this is very important because we want our large model to learn to have the scientific parameter, have the engineering significance of those data. And second step is pre-trained buildings. This is a supervised learning in AI field. We have pre-trained the model because it's size GPT based, and fine-tuned the model as such GPT enhanced. So you can see in this process, they also have this fine-tune model on this step. And then the third step is fine-tuned models of transfer learning, which makes this model be active from one building to the building clusters. So this is a low, also using important, so important is trainable weights of the specific location with SciGPT. This is one of the core part of the large model, and also using the low rank adaptation. Okay, here is the parameter of the SciGPT. Different from the like ChatGPT, we call it a large parameter model of that size. For example, in China, there's a model as 236B, right? Our model for analytical, I do not need this model to be that large, right? So we even this we have this SciGPT has 6 billion parameters and 130 billions, and this data set size is important. This 120 TB. For I haven't mentioned the third core elements of AI, which is computing power. For this case, we're using 4 Nevada H8 machines. Okay, here comes the experiment. For this time's experiment, because it's quite early of this model, we use 2,000 buildings ranking from 2 to 20 stories, each subjected to 22 distinct seismic waves. We also evaluate the accuracy as R. You can see the performance of the 2,000 buildings. As a pre-trained model, the overall R can reach 949. And the best can even around 1. And for fine-tuned model, its accuracy can be increased to from around 2.5% to 3% for acceleration and displacement. So we think this accuracy is acceptable. And we also compare to the time history of low-rise, irregular, multi-block office building, and the middle-rise office building for the time history analysis. And here we just show you the analysis results of 20 campus building clusters for seismic prediction, and it can quickly have this response by but it's also we call it with high efficiency and high accuracy of this time history. It's totally different from traditional simplified models. And another professor, Professor Zhu, who's his group is working on the digital Tunji. It's a software. Except by also we have connected to each other. But more important, you can see the left part. We also train a large knowledge model. I will show you later. We call it Civil GPT. It has the knowledge of civil engineering background. If we ask a question, what the meaning of resilience rating, it can quickly answer the questions. It's also put at this platform of IS3. They call it IS3, and show the resilience rating results of the building, time history of the building. Okay. Okay, here comes the third part, third question. How to have the earthquake resilience assessment or rating? This is the last question because we have the big data and how to evaluate, right? So as introducing by Professor Campos Malario and Professor Martin Bruno proposed this resilience curve in the year of 2003. And we three have started this journal called Resilient Cities and Structures. The definition, one of the definition of resilience is the ability of a system to maintain or repeatedly recover its functionality after being disturbed. So this system can be the buildings, transportation. This is the first notes. Second is the function. We have to evaluate the function of the system. The third one is what kind of disturbance, like the disasters. The last one is how to evaluate the recovery. So before I started this journal, I really look at the low damage technology. We call it technology from an engineering point of view. But now I think it's very important for this new demand of the city. We start from technology to evaluate the economy and how to organize the resources of the city and how to protect our society to realize the resilient cities. So I show you the past technology quickly. One example is my point is from the one side is a low-rise wall, the other one is the braces, right? So those are very typical elements, structure elements. So how to realize the low damage? I do the research of the experimental analysis, modeling, and even build the full prototype structure. So these are three high-rise, we call it tall self-centering buildings by using of self-centering walls in China. You can see, although there the outlook looks similar, but the first one, number one, using replaceable coupling beam shear wall building. Second, using self-centering wall frame building. The third one, we use self-centering wall structures. This one, those are completed in the year of 2022. Hope next time I show you very close to Shanghai. But technology, I mean, the resilience is not enough, but how to evaluate this from after the earthquake scenario, after we obtain the damage, all the damages by using of the phase size former or ChatGPT models, but how to simulate the post-earthquake recovery and how to evaluate the resilient assessment is a challenge. So we proposed this resilience assessment framework recently. We call it the first is have to quantify the building cluster functionality, as I mentioned from the definition of the resilience. You see, the first layer of the city where the people live is the buildings. And then we have the following network like transportation, water, telecommunication, energy, and gas network. They have various of the configurations, but they fully supported the activities of the building layers. And from this kind of organization, we have the post-quick recovery simulation and to do the assessment, the resilience. So the first one, how to quantify the building cluster functionality. In our opinion, the role of the infrastructure system should be considered as support for building functionality. So which means the building clusters where the people live will be the central role of the whole cities. And infrastructure supported the activity of the buildings. So that's why we will have the preference in our system. We have the two measures. The first one is functionality measure one. We call it economic productivity. It's EP. EP of the I building equals to the EP of each, the unit area multiplied by the effective area of the buildings. From this, we can evaluate its economic productivity, and it can be calculated at each time in the resilience curve. The second is functionality measure two. It's defined as a service capacity because we define the buildings which has a higher preference, give the higher preference. So that's why we have the Q as a baseline, basic housing needs, and we have RSS is a relative importance of supplementary services to baseline occupancy. So which means for example, after the earthquakes, people can easily go back to their apartment with this area. So we call it the service capacity. Those are the two measures. And the second step is to simulate the post-quake recovery. Different decision makers can have various kind of recovery strategy. Like the shown on the right side, you can see we can choose like the fastest the shortest downtime or the lowest economic impact. There will be different curves, right? So we call it a semi-flexible recovery strategy, which combine the functionality quantification and dynamic optimization method. We call it semi-flexible. So in this semi-flexible recovery strategy, let's take Tongji campus, this campus map as an example. We're using graph modeling technology this time. In this heterogeneous graph, we have G in this graph. V means vehicles or nodes, represents the buildings and intersections in rows. And E, the edges represent the rows. And the recovery algorithm we propose have three parts. The first one is breadth first search, and second method is we put the road recovery first. We call it a minimum spanning tree MST module, and goes to the building recovery called dynamic optimization, and goes to the recovery parse. From this algorithm, the first step is a breadth first search, which has a time complexity of OV plus E. And this algorithm details is to introduce the temporal factors into the expansion points of each algorithm compared to traditional method. And the second step, we give the higher recovery priority of the roads, which means transportation is very important for the functionality of the community, which should be recovered, give the higher, the priority to connect the buildings right after the disaster. And the third is dynamic optimization recovery. We call dual model under resource constraints, and to combine the combination of buildings that can achieve the highest function increment of the each current time step. So those are the method we use for the recovery. And the last step is to resilience assessment. The resilience assessment of the individual buildings is different from the building class resilience assessment of the building clusters. So we introduce a probability in the analysis. At this shown at this like the how to say in this matrix, but also introduce multicolor simulation. For example, in the vertically, for the how to say for this column, which means resilient assessment of individual buildings. For the row will be the resilient assessment of building clusters in a single simulation, and finally the sum will be RP, the resilient assessment of building clusters with probability. From this, let's see the case study of the campus again. We have more than the 117 buildings, and we have transportation rows. So by using of this graph, we have the minimum spanning tree and the residual graph calculation, and also I introduce the contents of these national codes, which I also one of the contributor of this national code for the resilience. Okay, let's see the results. The preliminary results, you can see the road is given the first recovery, and then, excuse me, and the right side, you can see goes the resilience curve goes day by day, and the right bottom is repair labors after many days. These labors goes down rise, and this is one of typical examples by using of our resilience assessment framework. Okay. Here is a conclusion. Today I gave three questions, answer to three questions. I think disaster prevention and mitigation in complex systems of high density building clusters require the use of data and interdisciplinary research method. Based on the recent AI for science research paradigm, we re-look at all the past four paradigms, including experimental theory, structural dynamics theory, finite element analysis, and the big data driven research. Now we propose this phase size formal model for individual buildings and the seismic GPT model for earthquake safety prediction of building clusters. These models enable rapid prediction of building cluster responses and establish a method for building cluster seismic resilient assessment. For the future, we think we need to combine the following two. One is the intelligent prediction method, and the other is a resilience assessment algorithm to develop a seismic resilient maps for building clusters. And before I close today's my presentation, I have some byproduct of this foundation model, SciGPT. You see, they have ChatGPT. How about our knowledge in civil engineering? You see, these are human beings. We learn more knowledges in the past 5,000 years, especially for Chinese people, we have more than 2,000 years. But now we change our knowledge from the traditional knowledge points, knowledge, trees to knowledge graph. I do the research by using as a graph, right? We have knowledge graph. Now we can put the, train the AI understand, we call it a large knowledge model. So that's why the byproduct of SciGPT, we train this Civil GPT. It's not start from the pre-train. It's start from the fine tune by using of the foundation model. In China, we have more than 100 large language model as a foundation model. So we just put the token, let the AI understand the civil engineering. So because foundation model understand 29 international language, so which means our Civil GPT have very strong languages and also civil engineering knowledges. It understands, for example, 700 international codes and standard ASAE, ACI, like this. So this is free for you guys, and you can access by this website or this QR code, civilgpt.tunji.edu.cn. I think that's the future. We can share all the information and resources online. Thank you very much for your attention. And I look forward to your questions and submissions to the Journal of Resilient Cities and Structures. Thank you.
Okay, thank you very much to Professor Zhou for this very interesting seminar. And so now we have approximately 15 minutes with question and answer session. So I just remind to all the participants that they can write their question in their chat, or they can simply raise their hands if they want, and they can also put their video on. For those who are connecting through WeChat, we're gonna have transferred the questions directly on the chat, and I will read it so that Professor Zhou can answer. Okay, thank you. So let's see if there is anyone who has question. To the chat.
Quite clear, right?
Yeah, looks like I don't see. I was checking on the chat if there are any question from the chat. Okay, so there is a question from Andrea Casuta, who is asking, first is thanking Professor Zhou for the very interesting presentation, and he want to have a better or clearer explanation about what is the diffusion model.
Oh, thanks for this question. As I introduced at the beginning, I will have the access to show this algorithm proposed by the AI field, right? So especially from start beginning, like the machine learning, deep learning, and for deep learning, recently they have the like CNN goes to the transformer, and then one of the newest is diffusion model. Diffusion model I show you you have known the cases of Sora. It can have reduce the noise and give they give the graph or even have the videos. So that's why I also you see my idea for as an engineer, I refer to the field algorithm of the AI and introduce to our field. I also introduced this diffusion model to structure design as a generative design, which means I using diffusion model I train this model to understand the figures or drawings in the structure as a structure drawings, and it reduces the noises and to have the generate the structure plan layout of the elements. So that's why I propose this method we call the structural diffusion. After I completed these publications of engineering structure, this even this first the students published the first algorithm is in structural engineering. I read another question to him. Can we extend? Okay. Can we go back not only structure layout, let's go to like some architecture, give some drawings randomly, and you can quickly through the diffusion model again in combined with structured diffusion to have archi-diffusion. So which means the architecture gives some drawings quickly using the archi-diffusion become kind of layout of with architecture, and connected to structured diffusion have the plan layout of the structure elements and combined to the API of the software and do the analysis which meets the code requirement. From this one, you can see the future. We introduce a diffusion model, but the design analysis can become a kind of autonomous design. Thanks for your question. That's why I also using diffusion model. So
okay. There is another guy from the audience. Let me see if I can Disable the mic. Okay, Ahmed, I think you can speak on your own. If I allow you to speak. I see. One moment. Let's try again.
Hello.
Can you? No.
I
Man.
hear. Yeah.
Let's see. Can you speak, Ahmed?
Hello, can you hear me now?
Yeah.
Okay. You
Please.
go ahead.
Thank you very much for the presentation. I really enjoyed it. I would like to ask you just simple questions. So what do you think of the transformer-based models that are fed through the transformer-based model, I mean, and what do you think of the forecasting accuracy, and how about the amount of data for training? So generally, I'm asking in terms of what your opinion is. Is it a reliable model so far? Do we need more like community effort, as there was a community effort in, let's say, natural language processing? Do we have like acceleration, time history processing, like effort from the community as well? Okay, those were my questions. Thank you.
Okay.
Yeah. Yeah, thanks for the question. If I understand correctly, I think those, as I mentioned, those are those two or even three core elements for by using of AI is very, very important for our community. First one, we have to share the scientific or high quality data. In our field, I also, refer to the protein prediction. In their field, they do not have this kind of mechanism by using of finite element analysis. But in our field, we have the software, analytical and commercial software for finite element analysis. So that's why we can have kind of scientific data. But also we need like a in situ structural health monitoring data and like the shaking table test data to verify each other, which means we have more high quality data. So I think data will be kind of resources our community have to share. I have to make some advertisement now. Next year we plan to have we call it the data bank for research under the State Key Laboratory if you are interested. The second is algorithm by using of the transformer. Yes, now transformer is good at a parallel analysis. It's similar because between the natural language processing and our earthquake engineering because of the sequential architecture. But it also have the problems like the time, we call it time complexity. It's still not as efficiency as we expected. Now my students propose a new architecture. We are trying to see if it has a better solution to improve this algorithm. The last one, of course, computing power. We cannot rely on the large models, which is really not only its energy consuming, it's energy consuming process to train a large model. Maybe in the future we will refer to the small parameter models. That's the problem or current state of the art of the transformer. So you see, as you mentioned, from the data to the transformer algorithm and even to the computing power, we have to collaborate in the future for our community. Thank you very much.
Okay, thank you. There is one more question now from Zhang Yangxi. I will allow her to speak. Let me see. Okay, go ahead.
Okay, thank you.
Yep.
Thank you very much. It's Professor Joe. I'm Jianyun Shi from Jiaotong University is very close. Yeah. So
Wow.
my question is so did you take the hysteretic curve into account in your model? It's just is for different material like concrete, steel. The constitutive the model or law is very important. How can you put the constitutive the law into your the model to fit the all kinds of the structure? I mean, so the transformer model in your research is only for a specific building a structure, or can fit all kinds of other kinds of the structure still. So thank you.
Thank you. This is also a very important question because you see, for my research at the beginning, I just wanted to accelerate the analysis or calculation by using of finite element calculation. So finite calculation for each element, right? We have kind of material. This material, if it is entered the nonlinear stage, it has its own skeleton curve or historical roles for this for nonlinearity. That's true. For the accuracy, we should introduce those kinds of material nonlinearity to our analysis. But at the first stage of our analysis, from this, you see, that's why we call it a large parameter model. From lots of data, lots of information, we call it a physically informed data driven. In case the data is large enough, which means the model is large enough, and also the ground motion input or even the responses of the nodes is large enough, this large knowledge model can have quite good accuracy. This is one way because of this. This is that's why they have the emergency. I mean the intelligence emergence of this large model. On the other way, we also have the feeling that if we have obtained the nodes, the responses of nodes with this kind of efficiency and accuracy, in the future we should know more about the responses of the elements or even our structure members, like the walls, the columns, each walls, each columns. So next step, we wanted to introduce a GNN, you see, which is also shown on the screen. We combine the GNN and transformer. For the GNN, we would like to do the analysis of the member level. For transformer, it goes to the whole structure, level. So we will combine those neural network. Let's look forward to the future research and the discussion with you. Thank you.
Okay.
From Shanghai Jiaotong University, right? Thank you.
Okay, thank you for a response. Okay.
Thank you. Now I'm reading a question that's coming from WeChat. You are introducing the artificial intelligence technology, which is competitive with ChatGPT. He wants to know more, and if you can share the code use that you can make it open source for the research community. That was the question.
Thank you.
Yeah.
It's okay. Let me show you. Yeah. Here is the Civil GPT. It's from how to say why I call it a byproduct of Science GPT. It's not start from the pre-trained. It's just a fine-tune. Fine-tune is very typical for the model. It's not that so that's why now that's fundamental. So that's why it's important. It's data. So actually, Civil GPT, which is a civil engineering, Civil GPT learns all the data or token of all the knowledges for undergraduate students at 20 University of College of Civil Engineering. That's why it have a lot of information. It also can calculate the mathematics. And also it understands 3,000 codes in China, and 700 codes, international codes. That's all the knowledges. But as a people or the human being, we have the knowledge update, right? We in the next step we will train this Civil GPT to understand the handbooks for the more advanced, like the PhD or the postdoc students. So that's why it's not important to share the codes. I mean, the most valuable is the data, is the knowledge, but you are welcome to use it for free. You just register for Civil GPT by use of the email account or the cell phone number in China. That's both are acceptable. Thank you very much for your attention.
Okay. I don't know if there is any more question from the chat or from the audience online. If not, since I think we're almost done with the time, we're running out of time. The answer, additional answer to questions you can find always in the journal Resilient Cities and Structure. So I encourage all of you to watch your email, because there will be more seminar in the future coming out. And again, thank you very much to Professor Zhou for his contribution and his wonderful presentation. Thank you.
Thank you. Yes, thank you, Professor Malario. Thanks for everybody, because this is December. This will be the last webinar of the year. Wish you all Merry Christmas and Happy New Year. Thank you very much.
Yeah,
See you next.
Happy New Year to all of you as well. Bye.